morning, ladies and gentlemen. My name is Noah Johnson. These are my teammates, Thomas Malton and Nicholas Morello, and we are Team AstroNova. We're here to talk to you today about the portable waveform generator, or as we like to call it, the WG800. Now, 6 months ago, we set out to create an updated replacement for AstroNova's current 2-decade-old marketing tool, the handheld waveform generator. This failed in several areas because it lacks key features that nearly every waveform generator on the market has these days. The output amplitude was fixed, the frequency adjustment was imprecise, and there were only 4 output channels, whereas most, if not all, of AstroNova's data acquisition systems have at least 8 inputs. Most alarmingly, there was no GUI or user interface of any sort. Now, all of these things combined made it very difficult to use the tool if you were not intimately familiar with it. Now, the new generation of tools made by us had to fix all of these issues while remaining small enough to hold in the hand and cheap enough to mass produce for the marketing team. Now, after 6 months of hard work, we are proud to present the WG800 prototype model. Here we can see just how much has changed between the two models, and the difference is marked. The WG800 prototype is a culmination of nearly 1,500 man-hours of diligent engineering work. It supports user-specified generation of a multitude of waveforms, including sinusoid, pulse, and square waveforms, as demonstrated here on AstroNova's TMX data acquisition system. Now, over the past several months, we've spent quite a bit of time working on this project. In the past few weeks, we've worked on verifying our outcomes and seeing if we've really met what we've decided to do here. And out of 28 outcomes that we originally set out to complete, we've fully accomplished 25 that fall into the categories of hardware, firmware, software, and PC application development. Now, all things considered, we believe that it is fair to say that we, Team AstroNova, have fully accomplished our best outcome. Now, let's consider these key accomplishments that I just mentioned a little bit more, starting with the internal design of this device. Now, those of you who attended the Fall Summit will remember that we ambitiously decided to use an FPGA in this design. The upside of that choice was that it allowed us to tailor the architecture to our needs. Although the downside was that meant that we had to write it from scratch for the most part. Fortunately, members of our team have quite a bit of experience with this sort of a situation. So, starting with a single-channel sine wave generator and slowly building all of the necessary features on top of this model, an elegant and powerful solution emerged. The final architecture supports 8 phase-locked outputs, a lightning-fast 10-second boot-up time, and fully custom arbitrary waveform generation and storage. But this is only one part of a much larger hardware design. And for that, let's hear it from Thomas Malton.
Thank you, Noah. The evolution of the portable waveform generator has drastically evolved over the course of our project. This evolution can be seen to the right, starting with AstroNova's 22-year-old product and progressing to the working prototype of the WG800. We began the project by analyzing the WG800's obsolete predecessor and selecting components that would allow us to reach or exceed our goals. With the help from AstroNova, we used these components to create a schematic for our custom PCB. While our PCB was being fabricated, we utilized an RD evaluation board to demonstrate a proof of concept and enable preliminary software and VHD automated development. After receiving our board in early February, we ran tests and verified that performance matched our goals. AstroNova now has a prototype of the WG800 housed in a customized off-the-shelf enclosure, but this alone wasn't enough to complete the design. The user needed a way to interface with this hardware. With that in mind, C code was developed to target the microBladesoft processor. The development of the embedded software was a challenging task that we were excited to face. One of its main jobs was to handle the user interface for the local control. This user interface paved the way for many improvements over the previous model. The local control enables the operator to have fixed control over the frequency and amplitude using a 1-2-5 method. In addition, it offers the ability to cycle through 4 banks labeled A through D. These banks can also be selected to view the 8 waveforms that reside inside them. And lastly, the local control includes the reset to defaults option. The second job of the embedded software is to perform tasks behind the scenes. These tasks include waveform creation, data storage, post-communication interpretation, and battery monitoring. The waveform creation uses algorithms to create triangle and sawtooth waveforms. The data storage enables the WG800 to return to its previous state when the power is cycled. The post-communication interpretation allows the PC to have advanced control over the device, and the battery monitoring notifies the user when battery voltage is below threshold. When this notification is displayed, the outputs will be disabled and the backlight will turn off after a few seconds to conserve power. This will remain true until external power is supplied and the operating voltage is once again above the threshold. I will now hand it over to Nick to talk about the PC application and our future recommendations for this project.
Thanks, Tom. So our last key accomplishment was PC-based host control. We decided to go with Microsoft Visual Studio and C# coding language to make this happen. We used a Windows Form-based application. Our basis for this application was to provide greater and more granular control over the WG800 through a simple user interface pictured here. At the top of our app, we have the master frequency and amplitude controls. If the user clicks one of these buttons, they can specify the exact frequency or amplitude that they would like the WG800 to output. Moving down to the left, you can see our bank drop-down selector. This tells the user which bank they're currently in. Below that is the Restore to Defaults button. When this button is clicked, all banks return to default settings as specified in the documentation. Moving over, we have the channels. When the user clicks the channel, a submenu pops up of predefined waveforms of which they can select. Once selected, this information transfers directly over to the WG800. If the user is in Bank D, they're able to select specific parameters to that channel, such as frequency or amplitude. In the middle is where the selected wave is displayed. Off to the right, we have the Parameters button. This is only available in Bank D and is designed to show the different parameters set up by the user. Beneath that is the Connect button. Before connecting, the user must specify the COM port that the WG800 is connected to. Now, although we achieved our best outcome, we believe this product has much greater potential. After reviewing the WG800's capabilities, we came up with a few key improvements that could be accomplished given the appropriate time and resources. First, if we had wireless connectivity, we would be able to ditch the bulky LCD display and have a smaller enclosure overall. Next, if we worked on the noise reduction, it would help with our waves at higher frequencies. Also, the size of the system architecture could be optimized in order for more arbitrary storage or better output precision. Finally, the embedded software could be optimized. Thank you for everyone coming today, and thank you to our technical directors, Dave Kordick and Chris Tate, and a special thank you to Dr. Sunak.
Thank you.